This was the topic that I knew least. Back when I was studying for my CCNA more than a decade ago, I knew the major concepts: subnetting, network address translation, blah, 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 all of those things. But I knew there was this weird one called spanning tree, something about loops in a network. I knew it was good, it helped us, but it just was something that automatically did it all. And I was like, well, it was one of those things that just didn't feel important to me. So I didn't really learn it that well. I guess I knew it enough to get by the exam, right? So whatever that means. The exam 12 years ago now, which is nothing compared to the exam that is in modern day. So now, fast forward 12 years, and if someone were to ask me, so do you still feel the same way? Oh, like with the amount of complacency that I thought about spanning tree before, like I've flipped exactly the opposite and be like, what? What was I thinking? Do you realize how huge spanning tree is and how fast a poor spanning tree design can, at best case, just make your network miserable, but at worst case can take the whole thing down? That's the spanning tree world. So we're going to look at what spanning tree is all about, some good switching practices, what switch loops are, how to stop them, and then the specifics of how spanning tree really works. Fact: redundancy is good. You agree? In technology, the mantra is 2 is 1 and 1 is none. Single points of failure want to be avoided as much as possible. Look at this picture. It's Network Town, USA. It's a normal business network. Throw in some happy servers and computers and users. They're all doing their thing. You got a router here going to the internet that people are accessing, and everything looks good. But then you start thinking about it. You're like, you know what? If this switch goes down, or this port goes bad, or this port goes bad, or this cable gets disconnected, or same thing here, we essentially lose the bulk of our network. Everybody dies except for these guys who still have the ability to get out, but they can't access the servers they need and all that. So you think, well, this has a simple solution. I just take a network cable, go click, click, right? Redundancy. Now I can have this guy go this way or this way should something have failed in between there. That makes you feel good until you realize you just took down the whole network by doing that. Why? Well, because of how a switch handles a broadcast. When this computer sends a broadcast message, a switch will do what with it? Send it everywhere. Out this port and this port. Received on here, goes out all its ports, so this guy gets it, this guy gets it, and so what you end up with is these broadcasts that just start looping round and round and round, faster and faster and faster. I can't draw that fast because it's going at the speed of light, taking down every single device that's attached, and it just gets worse and worse the more broadcasts that enter this loop. It's called a broadcast storm. It's a bad day when that happens. So everything on the network's down. All of the computers freeze because their processors are spiked at 100%. The switches are locking up, dropping packets, rebooting themselves. I mean, it's a bad day when that happens. And we all had good intentions. We're like, I just wanted some kind of redundancy in this network. So we walk away from that thought going, well, okay, I guess in switches anyway, redundancy is bad. We don't want that. And then you happen to go to Cisco's website and say, well, how do you say to do it, Cisco? And Cisco comes out and says, well, actually, this is our switch layer design, to where you design it in terms of modules, to where you have your switches here where computers plug in and access the network. And those have redundant links to their upper layers called the distribution switches. And the distribution switches have redundant connections to core. I mean, let's ask, is this redundant? Could we have loops in this network? Oh, yeah. I mean, look at it. I mean, one broadcast, shoop, 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 shoop. I mean, this is redundancy heaven, where everything is redundant. So if this is Cisco's design, if this is their best practices, then how can we have the redundant connections eliminating that single point of failure and not blow up? I know you're smart people. I know you've seen the title of this nugget, so you know what the answer is. It's spanning tree protocol. So again, to restate the issue, switches forward broadcast packets out all ports by design. And yet, redundant connections are necessary in business networks, but if we just leave it as is, those broadcast packets will loop around and take down the whole network. We can't have that, so we have the place of spanning tree. Spanning tree drops trees on redundant links until they are needed. I know, sounds cheesy. Enter the tree. I've found that spanning tree is one of the most forgotten topics, maybe just because STP is a motor oil, it's the Stone Temple Pilots. There's so many things that STP stands for. Maybe it's just the acronym chaos, but nonetheless, I had to have just a simple analogy. Spanning tree, we'll take a tree. I know, you didn't think I could animate, did you? Check that out. I'm taking this tree and finding the redundant link and thunk, dropping a tree on it. So what's the tree represent? It represents being disabled, as in it is no longer in use, so these guys can communicate, and yet you have the good, warm, fuzzy feeling of redundancy taking place, because if this is ever dropped, if we lose that connection, spanning tree goes, shoop, yanks the tree off. So the tree is now, erected off of the line, and all the traffic can then flow on this line. On this line right here until the primary line is reconnected, and then working with this little tree, it's hard to do. And then it goes back and blocks the line again. So that is all there is to spanning tree. That is its goal. It is to block the redundant connections. Now you might be saying, well, why is it so complex? Why was this the topic that you avoided and didn't quite understand when you learned the CCNA, Jeremy? Because our networks aren't this simple. We don't have networks. I keep doing that. We don't have networks that have two switches with redundant cables between them. If they were, then spanning tree would be a 5-minute topic and we'd be done. Our networks look like this. So we come to the question of, well, okay, we've got redundant links, here and here and here and everywhere, and now you have to say, okay, spanning tree, come save my network, and it will, that's its job. Block the redundant links, but now you have the question, well, which redundant link is best to block? I mean, why would you block this one and not this one? Or vice versa, why would you block that one and not this one? Or how about this one? What's the best one to block? Now enter the complexity of spanning tree, simply because its goal is simple, but our networks are complex. Here are the key facts about spanning tree, essentially the engine behind how it works. The original spanning tree, 802.1d, it is old, but still is in widespread use. It's still the default version of spanning tree on just about every Cisco switch you pull out of the box. Was created to prevent loops, as we know. The way that it works is the switches send probes. These probes are actually called Bridge Protocol Data Units, BPDUs, to discover loops. Think of these probes like sonar, right? You're in a submarine, you go boom, you send out sonar. Like, that's either submarine sonar or the sound they play on the airplane to tell you to sit down. So boom, sonar beam goes out and it reflects back around all the obstructions around you, in the submarine or the ship or whatever's using the sonar is able to be like, oh, iceberg ahead, Captain, or whatever. They're able to detect all of these kind of things. So BPDU sonar allows this guy to go boom, BPDU goes around the network. Now these things they're actually multicast, but they're treated like a broadcast, to where it comes to this switch, rounds the bend, comes to this switch, and comes back to this guy. Now that BPDU is tagged with some very specific information about this switch. So say this is switch 1. Essentially, in a nutshell, inside of that BPDU, it says, I belong to switch 1. So what did switch 1 just discovered? He went, boom, and send the sonar. It goes around the network, and all of a sudden he sees his little bong, his sonar BPDU, come in another port. He's like, whoa! I sent that out this port, and I received it on this port. That means there is a loop in the network. So that's how they discover loops. Now this BPDU has a second function, and that is to help elect. That's right, they have a little political election here. Elect the core switch of the network, which we call the root bridge. Simplistic view of spanning tree. All switches find the best way to reach the root bridge and then block all the redundant links. So there is a set of rules that spanning tree lives by when it's operating. Clearing off of my arrows here. That says elect essentially the center of the network. I mean, put yourself in the role of, like, you just moved into a new neighborhood, and you know that every day you're going to have to go to the new office on Central Avenue. So you pull open the map and you're like, okay, man, Central Avenue, that's where I go. That's what I do. I go to work, and that work happens to be on Central Avenue. So I'm gonna have my house over here and look at the map, and I've got all these different ways to get to Central Avenue, all these different roads. But you know what? There's that one. And that is the fastest way to get to Central Avenue, thus to reach the office. And that's what the switches do. They elect the root bridge. The root bridge represents Central Avenue. Say it's this guy. All the switches are like, man, that is the center. That's the hub of everything in the network. We want to go there. So they all find the best way to reach that central of the network. Best way to get to Central Avenue. They're like, okay, well, man, this link is probably the fastest one there. And this guy's, man, he's like, that's the fastest one there. And then they go, okay, well, what's left over? That one. What are you? Dead. Blocked. That's where the tree falls. Flunk. So spanning tree, the biggest thing, I think at this point, the biggest thing I can communicate about spanning tree is it's not that complex. Now, I know it's like, well, wait a sec, you just said it was. Well, it is because our networks are complex. It may take some brain power to figure out what it's doing, but the rules, and this is what I gotta get you to catch, otherwise you're gonna end up like me when I was 10 years ago, trying to figure out spanning tree. I was like, man, this is just crazy. If somebody would have just said, look, there's some simple rules to spanning tree. 1, figure out where the center of the network is. 2, find the best way to get to the center of the network. 3, block everything that's not the best way to get to the center network. If somebody would have told me that 10 years ago, I'd have been like, oh, thanks. That totally clarified it for me in all of the tons of documentation of what spanning tree can do. So that's the high-level view. Let's dig a little bit deeper. I mentioned that these switches all send BPDUs, right? Bridge Protocol Data Units. And I said it's kind of like a switch identifier that tells this is my BPDU. It's how they detect the loops in the network. If you were to take that BPDU and rip it open with a packet sniffer, you would find out that there's 2 key pieces inside. One piece is the bridge priority. The second one is the MAC address of the switch itself. Not one of the MAC addresses that it learned about, one of the devices that are plugged in there. I mean, the switch itself has its own MAC address. It came from the factory that way. And we actually, when we combine these 2 pieces together, we call it the bridge ID. Now, here's how the story works. These switches, when they connect together, as a matter of fact, when they connect to anything, whether it's a computer, a server, a switch, a router, anything, they plug into anything, they automatically start sending BPDUs once every, count it, 2 seconds. So it's a lot. It's like, hello, hello, hello. It's sending out these little BPDUs trying to detect loops in the network. So every 2 seconds you get a little probe going around. He's like, yep, we still got a loop in this network. It's always doing that. And it does that. So, for example, I'm deleting my seconds there. For example, if this goes down, he's able to detect that within 2 seconds. Be like, wow, my BPDU didn't make it back. That must mean one of my redundant links went down. Maybe we need to do some recalculations on where the tree fell. So look at all these switches. What I've done is given you what bridge IDs look like. Now, this number right here, 32768, represents the priority. You might be like, why'd you pick that number? I didn't. It's the default. Every switch, when you pull it out of the box, has a bridge priority of 32,768. The range of that number goes from 0 to 65,535. You'll see that one quite a bit. It's a common number because it's 16 bits of data or so. So you might go, okay, this is just getting weird. Like, why? Come on, why would somebody grab a dart, throw it at a board, and decide on 32,768? It's kind of right in the middle of all that. What's the point? Well, by having it at 32,768 by the default, for every switch in the world, that's the default, or should be if they're following the standards basis. That means that you can, set things lower or higher to set their preference. So here's the rule. The root bridge is the one, and this is, I want to embed this one in your mind, with the lowest bridge ID. Lowest bridge ID. Now, let's talk this out. If all of these are 32,768 out of the box, and a lot of people set up networks not even knowing a thing about spanning tree, and so they just leave it that way, then everybody by default is tied, right? The priority is all the same, so that doesn't elect the winner, who the root bridge is. So what it does is say, well then I'm going to go with the lowest MAC address as the root bridge. So looks around here and says, okay, got 3s, got 2s, got 1s. You are the winner. Ding, 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 ding. You are the lowest bridge ID. You win. Now let me fill in a little information. If you leave everything by default, lower MAC addresses are manufactured earlier than higher ones. I'm talking like manufacturing date. So essentially, if you leave everything by default, the oldest switch in your network will become the core, the root bridge. So, I mean, it could be some little 10 megabit per second switch that you forgot about sitting in a closet somewhere, that you forgot to unplug. And that ends up becoming the root bridge. And everybody's like, oh, the center of the network. Let's all go to that root bridge. Now, you might say, well, why did they do that? Well, when they created the spanning tree protocol standard, they said, well, you have a choice. You can either go with the oldest one, the lowest number, or you can go with the highest one, like the newer, faster switches. And, initially you and I might sit there and be like, well, why didn't they pick the higher one, the faster ones? It seems like that would be the better way to go. Well, the problem with choosing the newer ones is then every single time you add a new switch to the network, it's going to have a higher MAC address. And it causes a network disruption because everybody's like, oh, new root bridge, and they start blocking and unblocking different links to find that root bridge, right? So by using the oldest MAC address by default, they choose the stability route rather than the performance route, I guess you could say. So with that being said, what happens is all the switches elect the root bridge. He ends up winning, and everybody knows he wins because he has the lowest BPDU. So he's the root. All of the switches light up one root port. The way they do that is by looking at what we call the port cost. Now, cost, I'll actually show you a slide on that in just a moment, where each one of these links costs a certain amount. Like, for instance, a 100 megabits per second is a cost of 19. So let's just say all these, just for grins, are 100 megabits per second. They're a cost of 19. They all see the full path because their BPDU passes through all of those links and calculates all of the costs as it goes. So this guy goes, okay, I can reach the root bridge at a cost of 19, or I can go 19 plus 19, so 38, and go that way. So he's going to say, well, this is the better route. I'm going to choose this path. That is now going to be considered my root port. Right? Same thing happens over here. He's like, this will be my root port, my port that I use to reach the root bridge. Now, next up in the list is the designated ports. Designated ports, this is again the rule. It is a forwarding port, one per link. So when I say the word designated port, you can just think of it as a port that is forwarding, a port that is working and sending data back and forth and all that. So the root bridge, its reward for being the root bridge is that it will always have all designated ports. It will never have, now here's a tip for you if you're ever doing show commands, a root bridge will never have a root port. Sounds counterintuitive at first because you're going, well, isn't he the root? Well, remember what the root port is. It's used to reach the root bridge. That means I go out that port to reach the root bridge. So you're like, well, obviously the root bridge doesn't have to go out a port to reach itself, so it wouldn't make sense for it to have a root port. Instead, it has all designated ports that is forwarding. I mean, even if you plug in a computer and you do some show spanning tree commands, you'll find out this is a designated port. It's nothing special. It's just a port that is forwarding. But the rules of spanning tree says there is only one of those per link. What does that mean? That means, for instance, this guy has a designated port. It means this guy cannot be a designated port. In this case, it's not. It's a root port, right? Same thing here. This is a designated port. This guy cannot be a designated port, and it's not. It's a root port. This is a designated port. This guy cannot be a designated port in terms of switching. So the point is, you can never have a switch with a designated port here, and a designated port here in the spanning tree protocol standard. That's against the rules. There must be only one of those per link. So in this little negotiation, we're now talking about this. They found their root ports. They're all reaching the root bridge. Now they have to let up the designated ports. So these guys go designated, right? These guys say, okay, we have to negotiate. Only one of us can have a designated port because that's what the standard says. That's what I've been written to do. This is the rule that I follow. So it says, okay, well, either I can have the designated port or you can have the designated port. So you might say, well, which one gets it? It's the one that has the best path to the root. That's a problem. Because this guy's looking, he's like, well, I've got a really good one. It's a cost of 19. This guy's like, oh, well, so do I. I have a cost of 19. So they're like, okay, now we're stuck. So now, who has the designated port? Well, if they both have the same cost to the root bridge, it's going to end up saying whichever one has the next lowest bridge ID. Now, this guy had the lowest. This guy has the next lowest. This guy is out in the cold. He doesn't get it. So this guy's like, ding, 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 I'm the winner. I get a designated port. I am the port that is forwarding. Now we know what some of you are thinking. You're like, huh? What? What? I thought this was blocked. How can you have a port that is forwarding when this thing is blocked? Well, in the way the spanning tree standard works, only one side blocks the link. Oh, and that's so confusing. You're going to be like, man, I get spanning tree. I'm totally understanding how this thing works. Then you're going to do some show commands, and you're like, designated? I thought this was supposed to be blocked. Only one side blocks its connection. It's this guy. He's the one where the tree fell, and it's him because he happens to have the highest bridge ID. Okay, I felt it on that slide. I know many of you, probably up till that slide, were like, man, why Jeremy say this gave him so much trouble 10 years ago? It doesn't seem like it's that hard. And then we hit that slide and you're going, what? Designated root 4? Huh? So let's bring it all back again to do one more example. I'm going to bring back that same simple topology, but remember it's going to be it's the same no matter how big and complex your topology is. Let's say again this has the bridge ID of 1, bridge ID of 2, bridge ID of 3. I know they're big. They're 32,768. These big long MAC address numbers. But just for simplicity, this guy is the lowest. This guy's the second lowest. This guy's the third, just like we saw before. How spanning tree finds the best path. I'm going to work through this as if, we started from scratch. Number 1, they elect the root. How? They all send BPDUs, right? Which helps them not only detect the links, but also elect to the root bridge because inside of that BPDU is their bridge ID, which exists of the bridge priority and the MAC address. So everybody's sending their little election ballot around. If we left it as the default, where this guy is 32,768, this guy would end up winning because he would have the lowest MAC address with the lowest bridge ID, however we got there. So he becomes the root bridge, right? So that's step 1. Elect the root because all of the switches find that as the center of the network. Now, once I do this example, I'm going to make it a little bigger and show you what some of the ramifications can be of picking the wrong root. So, second step, find the best cost to the root. So it's kind of like, election day, everybody elects the president, and it's kind of like, oh, okay, he's the president, let's figure out what that means. And so now all of the switches are like, we lost, this guy won, let's figure out what that means. I need to find the best path to him. He's my office. He's my central avenue. Let's all find the best way to go. So they use the cost. That's the first way that they find the best path to the root. They go, okay, and here's a quick cost chart. If the link is 10 megabits per second, then it's a cost of 100. 100 megabits per second, it's cost of 19. So, that shows you how it can work. Let's say this is a 10 megabit per second link. This is 100 and this is 100. Then it's going to say, okay, you are a cost of 100 to me, right? This is a cost of 19, so it's going to go, okay, well, this way in that case is better because a cost of 38 total, you following that, is better than a cost of 100 if I were to take that 10 megabit per second link. So that's where the bandwidth of those links really come into play. Let's just say for sake of this example, Let's be simple. Everything is a gigabit per second. So it's a cost of 4, cost of 4, cost of 4. So they all say, okay, the lowest cost is the one I want to go. So this guy says, this is my root port because it only cost me 4. The other way would cost me 8. This is my root port, and I go there. Now, what's this other stuff? Lowest bridge ID, lowest port number. That's where if you have ties. Let's say we've got a root. We've got something like this, right? We've got switch 1, switch 2, and then we've got switch 3. And let's say all of these are gigabit per second. They're all a cost of 4. So this guy's like, oh man, I can go this way and get to the root, and it costs me 8, and this way it costs me 8. So this is a tie. I don't get it. I can't break the tie. So then it says, okay, well, if it's a tie, then use the switch, choose the path that has the lowest bridge ID. So let's say switch 1 is, AAA, and switch 2 is BBB. Then he's going to say switch A is lower. A is lower than B in hexadecimal, so he's going to say, I'm going to prefer that path and go that route. So that helps break the tie. But you might be saying, well, then how would I get down here? Well, that one actually goes back to our original simple example, where I've got the root bridge, and I go chunk, chunk. Is that a loop? Yep. If a broadcast were sent, it would definitely, swirl around that network right there. So it says, okay, lowest cost, both of those are gigabit, that's a tie. Lowest bridge ID, they both go to the same place, that's a tie. Lowest port number is the one that ends up winning, which it says, okay, fast Ethernet 0/1 is lower than 0/2, so I'm going to use that path and block this one. You see? So this is all step 2. They're all trying to find the best path to the root. So those criteria right there are what allow them to find that way. Okay. Now, rule number 3, block whatever's left over. So once we've done this, once we find the best path, and I guess I should put step 2.5, enable one designated port. This was from the last slide. One designated port per link. But this just kind of happens. That's why I leave that out. So switch 1, and let's just say switch 2, switch 3, if that's how we're playing this. Switch 1 and switch 2 are like, well, okay, we need one designated port per link. Root is like, I got it. I've got the one per link. You're the root port. I'm the designated. Okay, I've got it. Designated port over here. So now when these two switch 1 and switch 3, negotiate, switch 1 is going to say, okay, I've got the designated port because, again, he has the lower bridge ID, so he becomes the one that is forwarding. And then switch 3 is like, well, I guess I drew the short stick. I will go ahead and block that link. If all our networks were only 3 switches big, the world would be a very simple place. However, they're not. And there's networks that look like this out there that we have to figure out and say, okay, well, who is the root bridge of this network? And then what does our forwarding path look like? And then does it really even matter in the first place? I mean, I know some of you might be thinking, well, good grief, this is a lot of complexity for something that happens automatically. Do we care? Yes, we do. Here's why. Let's just say that we've got this environment right here, and let me put some players in the game. First off, everything. Let's just say everything is gigabit per second links, which means a cost of 4. Right? We just talked about that. Second off, let's just say we left everything at default. The oldest switch in the network got picked as the root bridge. That happened to be this guy. He is now the root, elected by all of the BPDUs being exchanged between the devices. Now, for simplicity, we know the bridge ID is like 32,768 dot, and the MAC address, blah, blah. But just for simplicity, let's say this guy has a bridge ID of 1, 2, 3, 4. Let's just go 5 and 6, right? That's about as far as we'll go for now. So we've got all of these different devices. So obviously he became the root bridge because he is the lowest. Now let's watch what happens. All of the switches initially find the best way to reach the root bridge. This is going to be the root port, right? Cost of 4 to get there. This guy goes, okay, well, so I'm looking at switch 4 right here. I can go this way, it's a cost of 8, or I can just go shunk right there. Ooh, that's a cost of 4. This is going to be my root port. Right there. This guy, switch 2, goes, okay, well, I can go this way. Tunk, tunk, tunk. That's a cost of 12. 4, 8, 16. Oh, wait, that's nice math. 4, 8, 12. Or I can go chunk, chunk. So cost of 8, that's going to be my root port, right? So let's just stop in this little cluster for now. Those are all the root ports. Now, all the switches go into the next phase, which is picking the designated port. Now remember, the designated port, there is always one per link, one per segment is the official term. They're picked the same way that the root port is. Essentially, the root bridge has all designated ports. So it says, okay, designated port right there, designated port right here. That matches up to your root port and your root port. This guy, between switch 2 and 3, he goes, okay, well, I can be a designated port because there must be one per link, right? This is a link. And you're the root port, so I have to be designated. That's what the rules tell me to do. Now let's look at this one. Switch 2 and switch 4 are like, okay, well, this is neither a root port nor a designated port, so only one of us, now the rule comes in, only one is allowed per link. Only one of us can have a designated port. Who gets it? Well, again, just like the root port. One, whoever has the lowest cost to the root. So this guy goes, well, I've got a cost of chunk, or actually, scratch that. I've got a cost of 4, right? He goes, I've got a cost of 8, chunk. So he goes, well, then I guess I get the designated port because your cost to the root is more than me. Now, if the lowest costs were tied, then they would sit down and negotiate on the lowest bridge ID, and then it would just kind of pick the lowest port number between the two. To try and break that tie. So, one of those is going to end up breaking the tie. And so in this case, we've got this guy. He had the lower cost, so he became the designated. Up here, we've got switch 3 and switch 4. Both of them have a cost of 4 to reach the root, right? Cost of 4. You see that? So they're trying to figure out for this connection who has the designated port. So the lowest cost is tied. They're going to look at the lowest bridge ID. Now this guy has a bridge ID of 3. This guy has a bridge ID of 4. So ding ding ding, 3 is the winner. Lower bridge ID. He gets the designated ports. Right? DP. I'm running out of room. So those are all designated ports. Okay, I think we've got them all in that little group. So what's left? Block anything else. Block. Is that it? Block. Yeah, that's it. So essentially, if I take a snapshot of this, right? Screen cap it or whatever, because I'm about to make it ugly. This gone. Those links are disabled. This gone. That link is totally disabled. So our end switch topology looks like this kind of half figure 8, if you will, to where, for switch 4, which is a big switch, a lot of traffic going through, for switch 4 to reach switch 3, he has to actually go through the closet switch to get there. He's got, tons of bandwidth sitting there right directly connected, but instead, nope, this is the center of the network. All roads lead to him. So they have to go through each other. This guy can reach everybody, chunk. So, well, actually, he has to go chunk to get to switch 4. So you see what I mean? Everything kind of goes around that center of the network. So let's continue this on, beyond this little section. We've got switch 5 and switch 6. Let's start right here with switch 5. Remember the rules. He's going to say, okay, I need a root port. I could go this way. That'd be a cost of 4 and 8 and get there. Or I could go this way. Cost of 4, 8, and I get there. So, okay, costs are tied. Next up, lowest bridge ID. Well, I could go this way and I hit bridge ID of 3. Or I could go the other way and I hit bridge ID of 4. Okay, ding, ding, ding. We have a winner. This becomes my root port because he is a bridge ID of 3. And by the way, that automatically means this guy needs to have a designated port. There's always one per link, right? So this becomes the correct one. Now, between these two, they're going, okay, well, let's figure out, between us, which one's going to be designated, which is not. Switch 4 goes, okay, well, I have a cost to the root bridge of 4. What do you got? And he goes, 8. 4, 8. That's my cost. Switch 4 is like, I am the clear winner in that because I have a better cost. So I get the designated port. So what happens to that other link? Chunk, block. Right? You see how this takes some time and brain power? But if you remember the 3 rules, you're okay. Let's look at switch 6, right? Switch 6 is like, okay, I can go this way. Wrong color. Can't have green. I can go this way and get to the root, so that's a cost of 4, cost of 8. Okay, that's good. Or I can go this way and get to the root. Cost of 4, cost of 8. Well, actually, scratch that. I just went on a block link, so it'd be right here. Either way, cost of 8 to reach the root bridge. So again, we have a tie. So what am I going to do? I'm going to pick, this is tied. Let's pick the one with the lower bridge ID. Again, switch 6 goes, okay, switch 3 is lower than switch 4. So I'm going to choose this as my root port. Right? Now, also, I should mention, we do have options. We could go on each one of these links, from between switch 6 and switch 5 and down here, but that's just going to be an additional cost. We have direct connections. So this guy is going to end up being the root port. So automatically, this guy on the other side, shoop, he gets another designated port to allow that guy through. Same story as before. Switch 4 and switch 6, he's like, I've got the better cost. I get the designated port. This one, chunk chunk, ends up getting blocked. Wow. And this story goes on and on and on. What you end up finding, this guy blocks all his links. This guy has all designated ports, D, all the way down. So this, by the time it's said and done, you are able to find the flow of your network, but my word, how horrible is this flow? Everybody, you just feel it. These are our core switches. Tons of traffic should be going on those links, by the way. But instead, all of the traffic is coming down here. You just feel, coming down here, really kind of reaching that root, moving towards that center of the universe. So I know at this point you're just like, wow, this is getting messy. And yes, it does. You need a nice big schematic to do this. What's your point, Jeremy? The point is that the root bridge matters, right? The root bridge should be the biggest, baddest, most central switch in your network. Who is that? Him or him. One of those two. So what do you think our goal is? Our goal is to make the priority, that 32,768 number, we can change that. Make the priority less on this guy than on this guy. So now we'll look at the actual numbers in the next one. So maybe he's 1,000 as a priority. You can't actually use that priority, but for now, just go with me. He's 1,000 and he is 2,000. So he becomes the root bridge, and then everybody's like, oh, center of the network, almighty switch in the core. All traffic starts pointing to this. All the links naturally point to that. You don't have these weird things where distribution switches are kind of doing this whoop, to be able to get out, because that's where the root bridge is. You don't have that. Everything comes to the big bad switches, and this becomes a backup route. Now, there's no actual backup route term. It's just if this one fails for whatever reason, this guy takes over, and everybody's still using an efficient link. Wasn't it nicer with 3 switches? It's a lot faster anyway, but you can see that as long as you remember those 3 rules, the ones that I wrote up, lowest cost, lowest bridge ID, lowest port number, you can figure it out. It takes me time. If I have a big switch topology where I'm like, okay, what's connected to what? Okay, I've got the schematic. Okay, let's do it. Doing that full scenario, labeling every single port, it might take you 30 minutes. It might take you an hour to label every port and then really get the feel of which ports are actually forwarding. That's just the complexity of having a big switch network. So, we have seen some good switching practices. Redundancy is good, yes? Yet, redundancy will cause switch loops anytime you have them. That's where spanning tree comes onto the scene. Switch loops will be blocked by spanning tree until they're absolutely needed. So then we looked at how spanning tree does that in all its complexity, looking at the root bridge election, root port selection, designated port selection, and then blocking everything left over. Good. More on this to come in the next nugget. For now, I hope this has been informative for you, and I'd like to thank you for viewing.